Welcome back. So, when you last heard me, I was talking about net forces being applied to objects. Force equals mass times acceleration. Just stop. Hi, welcome back. So, last thing we talked about in the last PowerPoint and little movie thing with me in it was to get an object to change its motion, you need to apply a net force, an unbalanced net force to it. So as you can read on the slide over here, what happens when that net force is applied? The object's velocity changes. There's a name for that. We have a name for changing velocity. I'm going to let you guess it. It begins with the letter A. Have you guessed it yet? Guess I'll hit the button then. Maybe. There we go. Acceleration. I'm hoping you did guess it. Net forces cause accelerations. But how much acceleration does a net force cause? That's Newton's second law. It depends on how much net force there is and how much mass that net force is acting on. I'm going to explain it to you. Give me time. All right? And yes, this is going to be math. Yay, math. Okay. Newton himself, Sir Isaac Newton, figured it all out. Came up with an equation to explain it and named it his second law of motion. Oh, that went too far. There we go. So, without any further ado, Newton's second law of motion. And this is the part where you start writing on the note sheet now if you printed it out. If not, then you have your own piece of paper. Here we go. Acceleration of an object depends on the mass of the object and the amount of force acting on it. Pause, fill in those two blanks on your notes or write it all down on your paper, then come back. Welcome back. All right, in equation form, it is F equals ma. F stands for force, measured in newtons. M stands for mass, measured in kilograms. And A stands for acceleration, measured in meters per second squared. Caught up to me yet? All right, here we go. If you rearrange it, you get what Sir Isaac Newton actually came up with first. He came up with it in this form. Acceleration equals force divided by mass. Okay, we'll take a closer look, because if you see, that's a fraction. Oh, I know y'all love fractions, don't you? We all love fractions. So, if acceleration of an object equals the force acting on it divided by the mass, then I'm not going to hit the button yet. We're going to think. Force over mass. This is already written on your notes, by the way. Force over mass. It's a fraction. Force is at the top of the fraction. That's called, not a math teacher, but it's called the numerator, I think. So if the numerator of a fraction gets bigger, the value of the fraction gets bigger. Example, 3 over 1 is bigger than 2 over 1. 3 is bigger than 2. 5 over 1 is bigger than 4 over 1. 5 is bigger than 4. You get it? If the top part of the fraction gets bigger, the value of the fraction gets bigger. The top part of this fraction is force. So more force causes acceleration to increase. More force, more acceleration. That's the mathematical way of telling you something you already knew. The harder you hit something, the faster it moves after you've hit it. The harder you hit the gas, the quicker you get up to 60 miles an hour. Makes sense. Now let's do the part of the fraction you all hate. The denominator, the bottom part of the fraction. If the bottom part of a fraction gets bigger, the value of the fraction gets smaller. 1 over 1 is bigger than 1 over 2, which is also bigger than 1 over 3, which is bigger than 1 over 4. The bigger that bottom part gets, the smaller the fraction gets. The bottom part of our Newton's second law fraction is mass. The more mass, the less acceleration. But again, this is kind of a dumb moment if you think about it. If I kick this toy Bronco, SUV? I don't know what it is. Actually, it's a transformer, but whatever. If I kick this with my foot, it will accelerate a lot. If I kick a real-sized one with my foot, I'm gonna break my foot. What's the difference? The mass. More mass, less acceleration, assuming the same amount of force. Okay, here we go. Let me ask you a question. If I put a force on an object, it accelerates forever, right? Nope, it does not. It's only accelerating while the force lasts on it. So if I throw a football, it's accelerating while I'm throwing it, while it's in my hand. As soon as I let go of it at the end of my throw, it's going to stop accelerating. It's not going to stop moving, but it's going to stop getting any faster. And now it has a new velocity. As soon as the force stops, the velocity stops changing, and the object now has a new velocity. Make sense? Yeah? Take your foot off the gas, the car doesn't speed up anymore. Yeah, there you go. Alright. Reality check. Do forces cause motion? Pause. Say yes or no. Come back. Did you get it right? Let's find out. The answer is no. Forces don't cause motions. Forces cause accelerations, which is a change to motion. Alright? Okay, you need an example. The Earth. The Earth is spinning on its axis. What force is making it spin on its axis? There is no force making it spin on its axis. It formed spinning on its axis. It's been spinning on its axis since it formed. What would stop it? Nothing. To stop it would be an acceleration. Negative acceleration, but still acceleration. That would require a force. But there's no force needed to keep it spinning because it's already spinning. Make sense? Good. Also on your notes is the other rearrangement of Newton's second law. Mass is force divided by acceleration. Yeah. So use that tomorrow when you use it on the practice sheets I'm going to give you. But not today. You've done enough today. Go play or something, okay? Bye-bye. The light's still on. Yeah, I play with my toys, so what? Bye.